So, good morning, everybody. Last time we discussed two positions of a moving plane. We have seen Schall theorem, which said the motion between two positions of a plane can most simply be obtained by a rotation about the pole. So we have seen how to determine the pole of the motion for two positions, graphically and analytically. And actually today I will just add one alternative method in determining the pole. But what we were doing. So in analytical treatment, we had a fixed coordinate system which we were showing by x and y, and we were representing the vectors using complex numbers. So let's say this is position number 1, where we call x1, y1, and the angular orientation as phi1, and the second position is x2, y2, and the angular orientation was phi2. So we have determined the location of the pole in the moving coordinate system. So the lowercase letters refer to moving coordinates. It was A1 minus A2 over E1 minus E2, where E1 and E2 were two shorthands for E to the I phi1 and E to the I phi2. So let's write this as 1. So E to the, well, let me say J is actually E to the I by J. So it's a shorthand. So this gives us the coordinates of the pole in this moving coordinate system. And since it's an infinite rigid plane moving from here to there, it has the same coordinates for positions number 1 and 2. No surprise. Similarly, in the fixed coordinate system, it's a coincident point and it has unique coordinates again. As we derived last time, it was A2 E1 minus A1 E2 over E1 minus E2. And actually, A's were complex numbers representing the coordinates of the origin of the moving coordinate system with respect to the fixed one. So that was A1, that was A2 in complex numbers. Okay. Any questions on this that we have seen last time? Now, I'll do another derivation or an alternative method to find the pole, which sometimes may be more advantageous to use. Okay. So we did this derivation last time. Let me start with the alternative method. First, I'm going to define the rotation of the plane, which is phi2 minus phi1. And actually, these are dependent on where you measure it from. Here I'm measuring it from a horizontal line. You could measure it from an oblique line as well, it should be the same. But this difference is always constant, independent of which reference you measure the angle. Am I right? So that might be better. You don't need a reference for that. And also, You have the displacement vector of the point. That's a complex number, okay? Which represents the vector, whereas this was a scalar. So this is actually, you can call it angle of rotation. And this is the displacement I would use in quotes vector, because we are representing the vector by a complex number. So delta is this. Okay, that's delta 1, 2. Again, it is not dependent on how you select the fixed coordinate system, okay? Because that's displacement, whereas A1 and A2 were position vectors which were dependent on the origin. So we will suppose that we have a vector. Let me erase those A's so that we won't mess the figure up. We will not need it anymore for the alternative formulation, and we remembered what it was. So let's have it like this. I will assume that Q12 is a vector that points the unknown for P12. So my aim is to determine what this unknown vector is, okay? It's pointing the pole. And we can see that if I draw this vector, this angle is going to be the same as the rotation of the plane, phi12. So if I were, there are very nice colors here as well. If I were to write this vector, it would be what this was Q12, I was rotating it by phi12. So the yellow one would be Q12 e to the I phi12. But it's not pointing down, it's pointing up. So I'm going to introduce a minus sign to it. So using this, if you like, vector triangle, I can say that the displacement vector, which we know, is equal to sum of this plus that. Okay? So Q12 minus Q12 e to the I by 1, 2. And this is what I'm trying to find. It's the only unknown. It's complex. The equation is complex as well, so I can solve for it. So what I obtain is Q12 is equal to the displacement vector for the complex number representing the displacement vector over 1 minus e to the I by 1, 2. So on the right hand side, I know everything. Displacement is given, or I can find it from A's or whatever. I know how much the plane rotates, so that I can determine the vector that points from the point I select at the initial configuration to the pole. Okay. So Q12 is pointing pole P12 from position number 1 of the selected point. And actually, if you would like to, for some reason, obtain pole from the second position, actually it's Q12 e to the I phi 12. So it's up to you if you need it, okay? So let me write this as well. So this was for that. Q12 e to the I phi 12 points E12 from position number 2 if you need it, okay? So this alternative method is actually relative, okay? Whereas the previous one, this one was absolute. We were doing everything relative to the origin of the coordinate system, and it was pointing the pole from the origin, or it was yielding the coordinates of the pole relative to the origin. Whereas this one is something relative, which might be somewhat more practical in certain applications. Any questions? How about the people from the remote? Are you able to follow it?
Yes, hocam.
Good. Any questions before I start solving examples using both methods? Okay, so let me start with the examples. Well, it says two positions of the moving plane are defined by 2 points. So that's example 1. A1 has the coordinates 0, 0. B1 has the coordinates 1, 0. A2 has the coordinates 2, 1. And B2 has the coordinates 2, 2. And we would like to determine the pole using the two analytic methods and also the graphical method. So can I use this to represent what we are doing? Did you copy the blackboard? I can't use that part. The camera is belong to there. So let me use it. And let's keep our formula. We are going to refer that. So 0, 0, 1, 0 is this. Let me use some other color. So that's A1, B1, and that's the position number 1. And A2 is 2, so it's something like here, 2, 1. And B2 is 2, 2, so it's vertical, something like this. Of course, it's not scaled. So that's position number 2. And I'm going to determine the pole by using 3 methods, this, and graph. Okay, so of course, I'm not given the origin of the coordinate system. Assume A is the origin of the moving coordinate system. I'll also show if I take B, what's going to happen for this example, okay? So assume A is the origin of the moving coordinates. So what I'm doing is actually in the initial configuration, lowercase xy is coincident with capital XY, which is fixed. And then it moves to here like this, okay? So it becomes like this, if you like. I'm sorry, that's x2, that's y2. So initially, capital XY and x1, y1 are coincident, okay? I need these because I'll get numerical results so that I can interpret what's going on, okay? So, A1, which is the position vector of the moving coordinates in position number 1, is 0. A2, which is this vector, is actually 2 plus r. Okay? And the initial orientation of the moving coordinate system with respect to the fixed one has 0 degrees or radians. So phi1 is 0 and phi2 is, what do? We take this and rotate it by 90 degrees. So it's counterclockwise, so it's positive pi over 2. So, well, let me compute E1, E2. E1 is, remember, e to the I phi 1. It was a shorthand notation. So e to the I 0 is unity. And E2 is e to the I phi 2, which is pi over 2. So it becomes simply an I. So I can now compute these two very easily. The location of the pole in the moving coordinate system is A1 minus A2. I'm sorry, there must be a mistake. In my notes, it says A2 minus A1 here, which I know is true because I checked the answers. So what I did wrong, yeah, I just copied it wrongly from my notes. Just check what you have from last week. It should be A2 minus A1. Absolutely. That's the truth. Okay. So it's 2 plus I minus 0 over 1 minus R. Of course, that's not a proper way of writing complex numbers. The denominator should be real, or you can represent it as a decimal, but to be able to do that, you have to make this real. So what do? Yeah, we multiply numerator and denominator by the complex conjugate of the denominator. You can just do it with your calculators. Most calculators can handle complex numbers as well. So if you write a fraction like this and type equal sign, you'll get the answer. But the magic behind it is you multiply it with the complex conjugate, okay? So if you do so, this becomes 0.5 I plus 1.5, I'm sorry, 1.5 I. That's not vectors, I'm sorry, complex numbers. So what happens is, actually, I know the position of the pole. It is 0.5 plus 1.5, somewhere here. Okay, in the moving coordinate system in position number 1. So that's lowercase e 1, 2 in position number 1. Now, in position number 2, this is my coordinate system. It should be the same point. Up. Now, the real axis is vertical now. Up. And we had 1 here, so 1.5. The vertical coordinate is the same. And this point had a real value 2. And then 1.5 pi in this coordinate system will come to the same point. So that checks, okay? Actually, it's the only coincident point for the 2 positions. So what I'm doing is actually, I have this, I mark this, then I move it here. Of course, because it's not scaled, it's not the same point. It was out, now it's in. But if you do it scaled, it will be the same point. So you can just rotate it like this as well, if you like. But it's not this one, it will be that one. And it should be the same point, okay? Physically, which we will check. So any questions on position of the pole in the moving coordinates? It's the only coincident point in 2 positions. This was how we derived this equation. Okay. Now, for capital P12, which is the coordinates of the pole on or relative to fixed coordinate system, it is A2 E1 minus A1 E2, hope this is correct, yes, over E1 minus E2. So if I substitute the numbers, 2 plus R times 1 minus 0 times R over 1 minus R. And this yields the same numerical answer because in the first position, the 2 coordinate systems are coincident. 0.5 R plus 1.5. No, that's not dynamics, I'm sorry. 0.5 plus 1.5 R. So it's the same point, okay? It checks. Any questions after here? So that's actually a numerical check of what we are doing. Now, what I'll do this time is, you don't need to, but just to be sure that what I'm doing is correct, this time let me put the origin of my coordinate system to B for the moving coordinates, okay? So I'll call this x1 prime, y1 prime. And here I'm going to have y2 prime, x2 prime, okay? No one tells me put the origin to A. What happens if I put the origin to B? Definitely, of course, numerically, this is going to change. This won't change because it's the same coordinate system. And we will see that physically it's the same pole, okay? So that's just an exercise. Let me do it. So I'll repeat everything for B. I'm just trying to convince you, okay? So select B as origin of x prime, y prime. Of course, this time A1 is going to be 1. Position vector of B1. A2 would be the position vector of B2. So it is 2 plus 2i. As you see, things seem to change. Of course, the angular orientations, they are same. Phi1 is 0. Phi2 is pi over 2. So still E1 and E2 are the same. E1 is 1, E2 is I. So I can compute lowercase p12, which is the coordinates of the pole, this time on x prime, y prime. So it is 2 plus 2i minus 1 over 1 minus I, which turns out to be negative 0.5 plus 1.5 R. Since x prime, y prime has a translation of 1 unit, when you transform it to this one, actually you will obtain the same point, okay? Negative 0.5 plus 1.5. It's not a surprise, okay? Or for this one, negative 0.5 plus 1.5, the same point. Well, since these numbers are different, let me also calculate capital P12. Of course, the numbers I'm substituting are different, but the result will be identical to this because I'm using the same coordinates. So, what happens is 2 plus 2i times 1 minus 1 times I over 1 minus I. So this turns out to be 0.5 plus 1.5 R. So it's the same pole, okay? This was the first formulation. Shall we try the second one, which is the relative formulation to find the pole? Or do you have any questions on this? Is there anything that's not clear? Yeah. This one? Yes. No, it's A2 minus A1. A1 is 1. A2 is this. So A2 minus A1. Okay? Any questions? Is this clear? Okay, then let me try to apply the alternative method and let me use this part of the blackboard. So I have the formula here. Now erase those. Again, I can use A or B, or actually any point on the moving plane, but just to convince you that it works for both points, I'll try A and B. Now, first let me calculate y12. Actually, our angle of rotation is 90 degrees, so it's pi over 2 radians. For A, displacement del12 is A2 minus A1, which is 2 plus I minus 0. So actually it's 2 plus R. So I have everything. The relative position of the pole with respect to point A in 1 or 2. Actually, it's with respect to 1. I'm sorry, not 1 or 2. Is the displacement over 1 minus e to the r by 1, 2. So it's 2 plus r over 1 minus r. And this yields 0.5 plus 1.5 r. So what happens is, if I start from A, this is my Q1 to get the same point. No surprise. 0.5 plus 1.5 r. We can do the same thing for point B as well, just to see it, okay? It is independent of the points. Whichever point we select, we should find the same value. So let me show it for point B as well, so that we will be convinced. This time, my displacement vector will be different because I will be using for A2 this, A1 this, okay? So I'm going to subtract from this. So it would be 1 plus 2r, okay? Displacements of different points are not invariants of the motion. It depends just on the point you select, and actually for the pole, the displacement is 0. We derive this first equation using that property, okay? So that's not surprising. Then Q12 becomes delta 1 to 1 plus 2r over 1 minus r, and this yields negative 0.5 plus 1.5 r. So this time this is my Q1 for point B, and it points the same pole. No surprise. So it doesn't matter which point you select, okay? Any questions up to here? From the remote people, can you follow it?
Takip edebiliyoruz hocam.
Good. And you can ask questions. We can hear you as if you're in U3. That's very good. Okay. The final thing I'm going to do is I'll find the pole using a graphical construction. And actually, it's much easier if you do it on a CAD software or GeoGebra than doing on the board. Let me clean it so that the figure will not mess up. And I'll also remove the coordinates because I don't need them. Yeah. Okay. So, of course, since it's not to scale, I'll just try to sketch it. That was B1, that was A1. So I'll just draw the perpendicular bisector of A1, A2. So I'll just sketch a line which you don't. Then I'll draw a perpendicular at the midpoint. But in most of the CAD packages, you just select the 2 points after you say draw perpendicular bisector. That's all. Okay. This line is just for me to guide it. And then this one. And this one. So if you like, this is what we call B12, the perpendicular bisector of the homologous points B. And this is A12, and we find the very same pole. Okay. Any questions on this? Well, pole is important in 2 and even 3, 4 positions. That's why I would like to stress it out. And I have another example, which is slightly different. Again, it's not a very general motion, so that we can intuitively also see certain things. I won't try A, B's, etc. I will solve it shortly in the next hour. Yes. Exactly, because from T you have to go -0.5 and then 1.5. Exactly, but what is different is positions of point B and positions of point A are different. Okay, so these make the difference. I'm not substituting the same A's and B's. Okay, and that's why this is the displacement of point B. This is the displacement of point A. They are different. Okay, A goes 2 in the real axis and 1 in the imaginary axis, whereas B goes 1 in the real axis and 2 in the imaginary axis. So the displacement vectors are different. And actually, just think it this way. You have an infinite plane. You could select any other point on it, and you can calculate its displacement. Okay? So it's not dependent on that. And actually, we derive this formula by saying displacement of the pole in between 2 positions should be 0. That was the point we used in deriving this last bit. Okay? Any other questions before the break? Okay. Again, this one can be an intuitive example so that we can decide where the pole is as well, not a general notion. Let's see this time. One is 0,2. B1 is 0,1. B2 is 1,2. B2 is 2,2. So what we have is something like this. That's my fixed coordinate system. This is A1. This is B1. This is A2. This is B2. So this is position number 1. This is position number 2. The scale is terrible, of course. This time I'll just apply the formula for point A. We know B is the same. Sorry? Yeah. There's a problem with this. It's 1, 0. I'm sorry. Yeah. And this is 2, 0. It's going to be real X. I'm sorry. And there's a mistake in my notes as well. That's the trouble. I just did a copy paste. And those are not correct. Let me just be sure from my original handwriting, because everything is calculated based on this. Yes, 2, 0, 1, 0. No, 0, 2, 1, 0. Yes, okay. So now for the method 1, A1 is 2i, which goes from origin to A1, and A2 is 1. And what happens? It rotates 90 degrees clockwise, and actually we can say that y1 is pi over 2, y2 is 0. Okay, so if you like, this is my y. Okay, so the location of the pole on the moving coordinate system P1, 2 is this one, A2 minus A1, which is 1 minus 2i over E1 minus E2, and what is that? Yes, that's true. It should be 3 pi over 2 or minus, because I'm measuring it not this way. Thank you. But from A, if you like, this is y1, which is negative pi over 2. Actually, it's also 3 pi over 2. Okay, thank you. That's why here I have a negative I minus 1. So this yields 0.5 plus 1.5 half. So what we are doing here is, actually this is my lowercase x1. This is my lowercase y1. So with respect to these coordinates, it is 0.5 and then 1.5. So it's somewhere here, okay? Lowercase p1. And it's the same here. This is, let's say, x2. This is y2. So half plus 1.5 half. Okay? That's the check. Clear? With respect to moving coordinates. Now, I will calculate capital P1, which is with respect to uppercase or fixed coordinates. Of course, the numbers will be different, but physically it will be the same point. So, capital P1 is the same formula here, A2 E1. So 1 times negative I minus 2i times 1 over over the same denominator, minus I minus 1. So this turns out to be 1.5 plus 1.5 R. So 1.5 plus 1.5 R, it's the same whole, physically, okay? But this time, none of the moving coordinates is coincident with the fixed coordinates. We don't need it. Still, it's a simple motion. We can deduce that the pole is here. So that's capital T1. Now we can use the relative method as well, which is Q12. This time Q12 is the vector with respect to the fixed coordinates, if you like, that points from A to the pole. Okay. So actually, I should do prior computations. Let me do that first. Not rush to this. So phi1, 2 is phi2 minus phi1, which is 0 minus pi over 2, which turns out to be pi over 2. So is it the case? Yes, it's rotating 90 degrees counterclockwise. And delta 1, 2 is A2 minus A1, which turns out to be A2 is 1 minus 2R. So I can compute Q12 as 1 minus 2I over 1 minus e to the I pi over 2, which is actually I. So that turns out to be 1.5 minus 0.5 R. So from point A, it is 1.5 minus 0.5 I. That's going to be 2, 1, 2, which points the same pole. So, any questions on this exercise? Is everything clear? So any given motion, we can find the pole. Oh, I was going to find it graphically as well. Let me do it too. So I'll just draw the perpendicular bisector of A1, 2. So it's going to be something like this. And then B1, B2. So this is perpendicular. And most probably something like this, B1, 2. So it will intersect at the same point. Okay. Any questions on this? This equation or how I draw it? Which both? This or that? That one. Okay. Now, Q is a vector that points from A1 to the pole. Am I right? So, I start from A1, I travel 1.5 and negative 0.5. And then I find the pole. Okay, so it's a vector from A1 to the pole. That's it. In the absolute coordinates. But it's independent of the origin. It's relative to A1. Okay? Good. Any other questions? Okay, then the next topic is actually principle of superposition, which turns out to be very useful in certain instances. Let's discuss it. Now, we are given two things. The motion of a plane in two positions, similar to what we keep doing, but I'm sorry, this is number one. Number two, we also have a mechanism. So we will not design the mechanism, but it is supplied. But by using that given mechanism, we would like to move the plane from position number 1 to 2. So this is what is required. Realize the motion given in number 1 by using the mechanism in number 2. So it's not a real design process, but it is very useful in many instances. And I'm going to show how this works. It's really very simple. So that rather than designing a mechanism from the scratch, you can use that if it's suitable for your purposes. So, the example is position number 1. So I will use the same numbering. Given 1, position number 1 is defined like this. A1 is 0, 0. B1 is 1, 0. Position number 2 is A2 is 2, 1. B2 is 2, 2. Actually, this is the first example we have solved. Now, what are the mechanisms? Actually, I'll use two mechanisms to realize this. The first one is rack and pinion. Do you know what a rack is? It's a straight gear. And pinion is an ordinary gear, ordinary circular gear. So actually, this is, the motion is rolling of a cylinder on a straight surface without slipping. And the other one is planetary gear. Fixed sun. And radius of the sun here is equal to radius of the planet. And actually, this is, if you like, rolling of a cylinder over an identical cylinder without slipping. So both are quite simple motions. Actually, what is the procedure? Actually, in doing that, we will first have to determine how much the given mechanism should move so that it's going to rotate the plane same as given here, okay? This is important. So when you have a rack and pinion, how much you should, and rack is fixed, let me also write. How much should I roll the pinion? Or for this one, how much should I rotate the planet? Definitely it should be the same as this motion. And this is our first example. We have determined that the rotation angle is 5/2. Okay. So in both pinion and the planet should rotate 90 degrees counterclockwise. So if I start with A, I will not draw a rack and pinion, but I'll just draw a cylinder on a straight surface. This is my initial configuration. Suppose center is O1 and this point, which is initially in contact with the ground, is C1. Okay? And then I had to rotate it 90 degrees counterclockwise. So actually, it's going to roll to the left. So position number 2 will be something like this. This is going to be your O2. And when this rolls 90 degrees, C comes to here. So I'll call this C2. So if you like, this is the line. This is the line. That represents the motion of the plane. Okay? And they have the same motion, but where is my A, where is my B? To find it, I'm going to find the pole of this motion, okay? And then coincide the poles of the two. So you can do it any way you like. You can either compute the coordinates and then find P12 using any of the analytical methods, or you could use graphical methods. Okay? Let me use graphical methods because it's very simple on the blackboard. So I'm going to have the perpendicular bisector of C1, C2. Let me just check my notes to draw it properly. Since it's not to scale, that's C12, and that's O1, O2. It's going to pass through like this actually. So I'll have my pole here, P12 of the given mechanism for the motion. What I'll do next is, I know pole of this motion. I'll just coincide the two poles. Then where A and B are will show me where I should put it. And if you do so, it's going to be something like this. In the initial position, of course, it's not to scale. It's just a sketch. A1, B1. So I don't know. You just weld it here, if you like, by two wires. And then when you roll this, it's going to come to here, which is the second position. Okay? Well, if you use a planetary gear, it's a bit more involved to find how much it should rotate, but the rest of the procedure is the same. So what I'm going to have is the sun gear, which is fixed. The planet having the same radius, and it should be circular. These look like eggs, I'm sorry. So I don't know, let's call this point O. This point we can see. Now, what do we want? We want 90 degrees counterclockwise rotation. Now, if I call this fixed sun 1, the planet 2, and the arm 3, the gear ratio is -1 because it's an external mesh. Omega 1 to minus omega 1, 3 over omega 1, which is 0 minus omega 1, 3. Remember, it was just the gear ratios, but we were subtracting the speed of the arm. So, if you like, we can also call these omegas as delta theta 1, 2, delta theta 1, 3, delta theta 1, 3, which are the amount of finite rotations. Then, if we substitute delta theta 1, 2 as pi over 2, we will find delta theta 1, 3 as pi over 4 for this condition. So the second position will be here at 45 degrees. So actually this was C1. This is going to be C2. Very bad sketch. So if you had a point C which was vertical at this instant, which I'll call D1, it's going to come to here. D2. Okay, so that the planet is going to rotate by 90 degrees. Then, again, you can find the pole either by graphical construction or by using the coordinates of C and D, using any of the formulas we have. We know pole of this. Coincide the two poles. When you roll it, you will get the same motion. So from A1, B1 to it will move A2, B2. Okay? That's straightforward, I would say. Now, after these, what I would like to discuss is, let's return back to the 4-bar. I'm sorry. Any questions, by the way? If anything is not clear, please feel free to ask. This point is, yeah, now it should rotate by 90 degrees. Okay, this is what I have. The gear relation tells me that the arm should rotate 45 degrees. So I draw this. D in contact here will come to here. Or if you select, I don't know, E here, it will come up. If you choose F here, it will come down. Because this is rotating 90 degrees. But it's rotating above C C is moving as well, so it's not a simple fixed axis rotation, it's a general plane motion. So you have to find, by using any 2 points which are suitable for you, the pole of this planet. Then when you find it, you have pole of this as well, coincide the 2 poles, see where A1 and B1 are going to come in this position. I don't know, maybe it's here or maybe there. Just weld it. When you rotate it, it's going to come to this position. Okay. Any other questions? Yeah. Definitely. Eskiden çenemiz düşerdi, şimdi maske düşüyor konuşunca. I'm sorry. Okay. Now, rec and pinion is the motion is the same as a cylinder rolling on a straight surface without slipping. Okay. So what I want is this should rotate by 90 degrees, which is the same as this one. Okay, in counterclockwise direction. So white one is the first position that I have, and I roll it 90 degrees, so it's going to translate to the left. And actually, you can compute the distance O1, O2, which is radius of the cylinder times pi over 2. Am I right? So you can calculate this distance. And if I'm not mistaken, it's something like 1.5 something something, or 1.6, but no, 3.13. So it's 1.5 something. That's why you will have an overlap here, like the metal emblem. But if it's larger than 90 degrees, it will go further. So what happens is a point in contact with ground in the first position will come to here. Then you roll it 90 degrees, so that a line initially vertical becomes like this, so that you have 90-degree rotation. Okay. Then by using C1, C2 and O1, O2, either the coordinates analytically or as I do here, graphically, you can determine the pole. Then take this motion, coincide its pole with this pole. You will find AB somewhere here, most probably, if I'm not mistaken. It has been a while since I offered this course. Then for a few years, Eres Hoca did it, including last year. So I just forgot where it was. We can compute it very easily, okay? Then you're going to weld it to this, and when you roll it, it's going to come to the second position. The same is true for planetary gear. Okay? Any questions? Good. Now, after these, let's return back to 4-bar. Now, we were designing a 4-bar for 2 positions of a plane. And what were we doing? We were selecting so-called circle points, that is A's and B's, as we like, on the moving plane. And depending on how we select them, we find A0 and B0 on perpendicular bisectors. So we are more free to select A0, B's, A and B, but we have restrictions on A0, B0. The brute force method, if you would like to specify A0, B0, or if it's bound in a place, is maybe you can just change the position of A in 2 positions and move the perpendicular bisector and try to have it within desired area. But that's not something smart. We have a smarter way. Can we select the center points A0 and B0 as we like on the plane, and then A and B would be on lines. Can we do that? That is, can we reverse the problem? Is it possible? Let me say it with another word. Can we invert the problem? Yes, how? How shall we invert the problem? Something inversion. Harf almak isteyen. The first letter is K. Exactly, kinematic inversion. So let's discuss this. So that's over the pole business, but we will use poles all the time. That's why it was important. So the next topic is selection of center points rather than the circle points. That's A0, B0, as we like. Because in some design problems, you may have more restriction on center points than the circle points. So, now, the solution, as you suggested, is invert the motion. Then what's going to happen? The circle points that is the moving pivots or A and B will become center points in the inverted motion. So this is original motion, this is inverted, and center points will become circle points. And on the inverted motion, if we apply our design procedure that we have developed, we will select the circle points of the inverted motion on the plane as we like, but it corresponds to selection of center points of the original motion. Okay? Then center points of the inverted motion will be on the perpendicular bisector, which is a line, which is more restricted, but it will correspond to circle points of the original motion. Okay? So, what happens in the inverted motion? For the inverted motion, I will use a prime. The location of the pole is the same as the original motion. Okay, it's the only coincident point between two positions. But what happens to the rotation of the plane when you invert the motion? The rotation becomes negative of the original rotation. So I'll call phi1, 2 prime as the rotation of the plane in inverted motion. It is negative of the original rotation. So other than that, the procedure is the same. So you can use the graphical techniques we have seen. And actually, we have a theorem for that, which says the poles are the same, but the rotations are inverted. I think I don't need to rewrite it. Now, for analytical treatment, we have an interesting equation. If you would like to find the pole of the inverted motion, okay? So let me write these and then we can take the break. Actually, it's the break time, but it's just 2 lines, okay? Let's finish this. So, for original motion, we have AK, which is a complex number, is equal to RK e to the I delta K. So RK is a real number, it's the magnitude of the vector, and e to the IK is the orientation of it. So what happens is for 2 positions, it's K equals 1 to 2. And we define phi 1 to as phi 2 minus phi 1, which is the rotation of the plane when doing the motion. Now, for the inverted motion, AK prime becomes negative RK e to the I theta K minus phi 1, 2. And actually, this thing itself is the original AK. So we have a negative sign in front of AK. And we can split this as a product as e to the I theta K, e to the I negative phi 1, 2. So I use this part in this. I'm sorry, there should be a minus sign in the front. So e to the I phi 1. That's it. Okay, so simple. So what you do is you can use this for analytic formulations to find the pole of the inverted motion. Any questions? You're right. Thank you. There should be a minus sign in front of this because of that minus. Thank you. Any other questions before we take the break? Okay. Up to now, we have seen rigid body guidance for how to move a plane from one position to the other for the 2 positions. Now, we will start seeing correlating the crank angles, okay, which is something totally different. That is, you have one configuration and then the other configuration in a 4-bar, for example. So to be able to discuss this motion, three planes and one is fixed. Actually, the 2 moving planes are now 2 cranks, and we also have the fixed plane. Now, important simplification in plane motion is the rotations are additive. That is, if you think in terms of dynamics, x, y, z, all the rotations are about z-axis, which is perpendicular to the motion of the plane. So that's an important property. In 3D, it's not, okay? Yeah. Okay. Still, I'm thinking I'm teaching in one of the P or G classes of our department when I turn here. So my font size is according to that. I'm sorry. Okay. Plane, motion, rotations, edit. Of course, when we say edit, we have to consider the sign. That is, if counterclockwise is positive, then clockwise is negative. So, if we have the motion of two planes relative to a fixed plane, we would like to determine the relative motion between the two planes. Okay. So, given motions of with respect to ground or fixed plane, find relative motion of one moving plane with respect to other. So now I will start with the two-page PDF document that you already have, and it was updated twice yesterday. One for a typo, and the other one was I just felt I should add something else. So what we are going to do is actually let me go over the procedure. So what it says is we have to determine the pole and the rotation of the first motion and the second motion. So what we will do is this. Suppose we have two cranks. So that's my A0, that's my B0, and what I want is, I don't know the crank length, but I want this crank to rotate an angle psi, and I want this crank in the same time rotate an angle phi. Okay, if you like, we could put 1, 2 as well. So actually, my intention is something like this. I would like to design a 4-bar mechanism such that when I rotate this crank a certain amount, say 60 degrees, I want this to rotate 45 degrees. Of course, because it's a linkage mechanism, not gear, if you rotate this half, this won't rotate half. Am I right? You're all aware of this. They're non-linear. So it's only true for the design angles, whatever they are. If you half them, if you double them, something totally different will happen. Let's keep this in mind. So what happens is, actually, if you sit in one of those moving planes and watch the other one on that plane, you will see that the motion of the other plane, of course, it's not the full motion for two positions, is again obeying Shaw theorem. That is, for example, if you're on this crank, you will see two positions of this crank can be achieved by a rotation about a pole, but this time the pole is relative pole, relative to a moving plane. Okay? So, what we will do is to find the relative pole, we have a procedure. So, we know how much they rotate and where are the poles of this motion, these two motions. I'm rotating this from here to there. Where is the pole? Yeah, that's it. It's making fixed axis rotation. So it's always the pole, or it's always the instant center as well. So that's I'm going to call P1 to prime. This time prime is not standing for inverted motion. We have nothing inverted, okay? So the notation is not all consistent. And this is P12. So P12 is for this crank, P12 prime is this crank. What we are going to do is we will take this line as a directed line, okay? So that's P12, P12 prime. Direction is important. I'm going to draw a line Y through P12 such that the angle P12, I think the order is wrong here. It should be P12 prime, P12 Y, because I will draw it through here, is, there's something wrong here. Let me just check my drawing. Yeah, the notation is incorrect. I'm going to correct it again. I have to draw a line through P12, which makes half this angle with this with a negative sign, okay? So we have a minus as well. So the thing there should be P12 prime, P12. This was line 1. Okay, I'm going to check these once again. I don't know why they are wrong, because that document has been in use for a while. So that's going to be your line 1. You will do the same thing for P1 to O. I think it means the angle between this and that. I'm sorry, I just misinterpreted what I had written. It should be correct because we keep using that procedure. So, no, it is actually not that angle, but it's the angle between this and the line we draw. Okay, I just missing. So we do the same thing for P12 prime as well. I'll take this as a directed line, take half of this angle, and invert its direction. So this angle is going to be negative psi 1 over 2. And this is going to be the line Z. This is line Y. So when we intersect these two, for our case, this is the relative pole R1, 2, when you watch motion of one plane from the other, but since it's a relative pole, its position is position dependent. So it's the position of the relative pole in position number 1. Okay. So this is how we find it. Okay. Let me write what it means. R1 to 1 is the relative pole between 2 lines in position number. So that superscript 1 shows that, okay, it's in position number 1. And it is very useful in designing the mechanism. So we will need it every time. And it's very straightforward, as you see. Just take this as a directed line. And the angle between this line and line Y is negative half of this. And between this line and line X, negative half of that. Intersect them wherever it may be down or up, depending on the angles. You find the relative. Now, using this relative pole, actually we will see 3 different methods to design a 4-bar such that when you rotate this phi1 to amount, this is going to rotate psi1 to amount. Okay? So, any questions on this before I start the procedure? Yeah. If psi1 to in smaller than phi1 to. Yeah, that can be. They can be parallel. The relative form may be at infinity then. But if these are not equal, either they will intersect somewhere down or somewhere up. If they're exactly equal, then the relative pole is at infinity. You will have something like a parallelogram, which is actually linear as well. Okay? Which is a special case. But in general, if they're not identical, then they will intersect somewhere. Down, closer or farther, up, closer or farther. This side, that side, this side, that side. I don't know, but they will intersect. Anyway, unless they're equal. Okay? If they're equal, still it exists, but at infinity. Any other questions? Okay. So we have the design procedures, and actually these 3 procedures have different parameters. That's why we have them. And actually in the 3rd procedure, we can also optimize the transmission angle. When we say optimize, actually the transmission angle at 2 extreme positions of the mechanism are equal. So that's called a minimax optimization. It's not the real optimum, but you equate the deviation from 90 at 2 equal at 2 ends. Okay. So let's start seeing procedure 1. Actually, I'm going to apply it on this figure. So, well, you all know that what is important for the motion is not actually the link length, but link length ratio. So, you can take this distance 1 unit. Whatever 1 unit is, it can be 10 centimeters, it can be, I don't know, 100 pi, it can be 5 inches, whatever, okay? So actually you normalize A2, A3, A4 with respect to A1, okay? So you can have a small 4-bar or a big 4-bar, but as long as the ratios are the same, it will do the same motion. So assume this is arbitrarily 1, whatever 1 is. Determine the relative pole, which we always have to do. It's over there. We are going to draw 2 lines through this point, which will have an angle in between, which is, let me name it, as, I don't know, what shall we call it? And it is psi1 to minus phi1 to over 2. Now, For our case, phi 1, 2 is positive because it's counterclockwise. Psi 1, 2 is positive, it's counterclockwise. I don't know which one is larger, but depending on which one is larger, this can be a positive or a negative angle. Negative angle means it should be clockwise. It should be measured clockwise. Positive means it should be measured counterclockwise. So I'm going to draw two lines, this point, and what I'm going to assume is this is positive. So I will draw my lines according to that. If it's negative, the names of L1 and L2 will switch, okay? So that you measure the angle from one. Important. You just draw two lines. I don't know, maybe you draw your L1 like this. Then if this angle is, let me call this L2. If this angle is positive, of course, L1 should be counterclockwise. No, let me call it pink. Let's say this is L1. Let's say this is L2. So this angle is alpha. What does it say? Select A1 anywhere on L1. So this line, you can extend it to the other side as well. Any point on this line is a candidate for A1. Any point on this is a candidate for A2. But as you see, actually, I on purpose draw them like this. They don't look very good. Am I right? But what you can do is, since you have drawn one of the lines arbitrarily and then measure the angle, just rotate it. Okay? And try to see a better position. And still, you can select A1 on this, B1 on this. So how many free parameters do we have? These are given. So is this angle. But I can orient any one of these angles as I like. Am I right? Which is one free parameter. The other line is defined by alpha, which depends on given parameters. Then I can select A1 on L1 and B1 on L2 on two lines, so two more free parameters. So I have three free parameters to change the design. Is this clear? That's something very good. Why? Design is an iterative process. You may just draw these lines, select A1, B1, check the mechanism. The two positions might be in two different branches. It's not working. You just move B1 or A1. Okay, it started moving from 1 to 2, but the transmission angle is horrible. Or the link lengths are bad. This is one of the cranks is 100, I don't know, or maybe 50. So by changing this angle and by moving A1 and B1 on those lines, you can change the design iteratively. So we have three free parameters. Clear? So this is one of the procedures, which was procedure number 1. Any questions? So that you are going to have many 4 bars or many 4-bar candidates. When you move this by phi 1, 2, this is going to rotate by psi 1, 2. Okay? Now, the other procedure is slightly different. Let me erase the figure fully so that you will have something clear. Again, we are given phi12 and psi12, and we will select A0 and A0. And what we will do is, we will just select the first position of P1, of P actually, which is P1. Okay. Then, of course, since psi12 is given, I know P2. So what I do is, I select this length arbitrarily. Okay, which you could call A4. So that's another design method. In the previous one, all the link lengths or link length ratios, A2 to A1, A3 to A1, and A4 to A1 was found from the procedure. But here, you select one of the link lengths, or if you like, A4 to A1 ratio. Okay? So you can obtain B2 by rotating this side 1, 2. Then you can draw the perpendicular bisector B1, 2. So that's another procedure. Of course, that's a bad drawing. I will ask you to do scaled ones of those as your second homework. Okay, after we finish all the procedures. So this is my B1. Then again, I can select something arbitrarily, which is the location of the relative pole this time. That's not something physical like the link length, but this is something I have to select arbitrarily on this line. Let's say I selected here R1, 2, 1. So I'm going to draw another line that passes through the relative pole and A0. And actually, this is the perpendicular bisector of A. Okay? In between the two positions. Now, what I will do is, I will draw a line, capital Y, which makes half of this angle in the opposite sense. So I will also assume both of these angles are counterclockwise as well, okay, in my sketches. So I will just rotate negative phi1, 2 over 2 and draw a line Y, and I can select A anywhere on this line. But this is not all. This is one, I would say, candidate location of A, but I should also draw a line X such that A0, R12, X, which is, I don't know, should be B0, R12, B1. That is actually outlined this angle, okay, and it's, you see, clockwise. So I'm going to draw the other angle, A0, R12, X in the clockwise direction, like this. So these two angles are equal. Let me see what I have called them in my notes. Gamma. So that angle is gamma, the same angle, gamma. So that is line X, and point A is at the intersection of the two, because cranks subtend the same angle at the pole. So this is going to be my point A1. So I have the 4 bar, okay, again. Of course, we still have the same trouble. The mechanism exists at the two positions, but the design procedure doesn't guarantee that the two positions are in the same branch, or the transmission angle is good, or the link factor ratios are good, etc. Now, in this procedure, we again have 3 parameters. One is we can change this length, therefore the location of D1, and also the initial angle, and we have arbitrarily selected R12. So different 3 parameters to improve the design. Okay, so this is like a recipe. You just follow it based on the principles we have seen up to now, and it's fully graphical. Now let's see procedure number 3 then. Any questions? Okay, then let's see procedure number 3, which also can optimize the transmission angle. Well, this time we select again A0, B0 as we like. This time I will select the location of A1. Let's say like this, arbitrary. Then by rotating this by Y12, I can determine A2 very easily. Am I right? Because this is a given angle. It's the design constraint. Now, what I'll do is, I'll do a kinematic inversion. That is, I will assume, let me use a different color. I will assume the crank is fixed, but B0 is capable of moving. So if this is rotating Y12 above the pole, for the inverted motion, what's going to happen? This is going to rotate negative Y12. Am I right? In the inverted motion. So let me try to make it a little more scaled. So that's the location of B0 in position 1. No, it should be in position 2. What am I using for this? No, I'm doing something wrong. I'm not reading what is written here. That's not what is asked. I'm sorry. That's not what I should. I'm extremely sorry. What it says is, assume B0, B is fixed in its first position, determine A2 in position 1, which is the position of A2 relative to link 4 in the first position. So what I'm doing is actually I'm fixing link 4, which is this crank that I haven't selected, but I know it should rotate by side 1, 2. So what happens is, in the inverted motion, so what I'm fixing is this link, which we don't know where it is. So that's going to rotate negative side 1, 2. And actually, this is drawn for psi 1 to being clockwise, okay? So it's negative, it's counterclockwise. So that I'll have something a little more meaningful, but it will work for others as well, okay? So what happens is actually A0 comes to here in position 1. And then you can draw this angle. This full angle, which let's call, I don't know, alphabet gamma. Delta, not a good one. I don't know, mu. No, it's not good. Let's call it mu. So that angle is mu. So that's location of A2 in position 1. And we have A1 here. I can draw the perpendicular bisector of this. I guess it says so. Let me check it. Yeah, B1 can be selected anywhere on the perpendicular bisector of A1, A2, 1. So I have to draw the perpendicular bisector like this. Let's call it A1 to 1. Okay. So you can select B1 anywhere on this line. All points are candidate. But if you want the transmission angle deviation from 90 degrees to be equal at the two extremes, just drop a perpendicular to this and select B1 here. Okay. In that case, delta mu1 would be equal to delta mu2. But it doesn't say that delta mu would be small. Okay, we have no control on this. But still, we have three parameters, like selecting the location of A1. So we can try to reduce this by different trials. Also, of course, still we have branching problems. Okay, which should all be checked by your homework number 0. You have to analyze the mechanism to see if it's running or not. Okay, now we have one more procedure to design the slider crank, which is actually extension of procedure number 1, which we can see next week. I just have 3 minutes and I have to rush. I have 301 class. And then we will also design a 4-bar depth centers, which is very interesting and simple. But let's stop here, unless you have any questions, of course. Questions? No? Then thank you.